Quantum entanglement is one of the most intriguing and perplexing phenomena in quantum physics. It allows physicists to create connections between particles that seem to violate our understanding of space and time. But what is entanglement really? These two coins are not entangled. If we flip this coin, it won't have any effect on the other. Each coin, when flipped, will have a 50% chance of landing heads or tails, and that's true no matter what you see when you look at the other. But what if we could do some magic trick to entangle these coins so that if one comes up heads, the other will come up tails, no matter how far apart they are? Let's say I give this coin to Alice and this one to Bob, just before they set off on rocket ships going in opposite directions. Alice and Bob are each under strict instructions not to flip their coins until they've been traveling for 10 years. When the time is up, they each flip their coin and immediately send radio signals to each other with the answers. But while those signals might take years to reach their destinations, the entanglement means that the moment Alice sees heads, she knows that Bob's coin landed tails, and vice versa. Alice doesn't have to wait for Bob's radio signal to arrive to know what it will say. Alice's coin had a 50-50 chance of coming up heads, but once it does, Bob's coin is tails 100% of the time. Because Bob's signal is still traveling to her when she finds out the answer, it's as if Alice has predicted the future. This might sound impossible, but it's exactly what quantum entanglement does to individual particles in experiments. Let's say you carefully prepare two particles in a lab to make them entangled. One way to set this up is to ensure that they will have opposite spins, meaning they'll line up opposite to each other in a magnetic field. Then, you separate the particles by thousands of miles and measure the spin of one of them. If you find that its spin points up, the others will always point down. Like in the coin example, whenever Alice measures the spin of her particle, if it has spin up, she'll instantly know that Bob's particle has spin down, or vice versa, no matter how far away they are. Einstein called this spooky action at a distance. Because according to his theory of relativity, no information can travel faster than the speed of light. You shouldn't be able to know anything about the other particle before a light beam with the information can reach you. Entanglement seems to throw this idea out the spaceship airlock. To be clear, however often it's described that way in science fiction, this is not faster than light communication. Just like with the coin flip, the state of the entangled particle in your possession is random. You can't know ahead of time if it's spin up or spin down. All you know is that when you measure it, the other particle will be the opposite. Even if Alice and Bob tried to agree ahead of time on some kind of code to use for a message, they wouldn't get to decide what message they were going to send. It would just be random gibberish. Well, we can't use quantum entanglement to communicate instantaneously. We can use it in technologies such as quantum cryptography and quantum computing, which we'll discuss later in this series. But how does it work? How do the particles know what to do? Are they passing messages that we can't see? And why can we entangle particles but not coins?
Entanglement is one of the most interesting and puzzling concepts of quantum mechanics. In fact, Einstein was one of the first ones who kind of dabbled in it, tried to understand it. In fact, he wanted to show that it was not part of our world, and then that quantum mechanics is not the correct theory. But his discussion was very wordy and kind of conceptual and not very practical. And it took another 20-25 years before an Irish physicist, John Bell, kind of turned his ideas into an equation. If entanglement didn't exist, the equation would be satisfied. If entanglement exists, it would be violated. The world is quantum mechanical. This is absolutely amazing. This is something we cannot understand with our usual concept of classical mechanics, but it is there, it exists.
Quantum entanglement is certainly strange, and we still don't completely understand it. But it is a feature of nature, and it's an incredible tool that we can use. The results of these experiments have applications in new technologies that will forever change our world. It isn't magic, but it might just be a little bit spooky.